Today we're going to look at section 14.1, which is our first section on the ANOVA test. Now, what the ANOVA test really does is it really is an extension of the difference of means test where it checks if at least one mean is different from the group. So if I have, say, three means, let's call them mu1, mu2, and mu3, three population means, it will test to see if at least one pair is different. Maybe these two are different from one another, but they're not significantly different from the third one. That would be a conclusion. You could also say the first two are different and these two are different and these two are different. They could all be different, but it just says there is at least one pair that is different. So that's when we'll kind of go through an example. We'll kind of go through hypothesis, the calculation of the test statistic, all that kind of good stuff. And then in a second video, I'll show you how to do it on Google Sheets / Excel. So the hypothesis for an ANOVA test are pretty simple. The null just says there is not a significant difference between all of the means or any of the means. So basically, we're saying they're all the same. So in that case, we say mu1 is equal to mu2 is equal to mu3 is equal to whatever, because really this works for three or more means. The alternative simply says at least one mean is different from the other. So we really don't have any mathematical system or symbols. We just basically have the words. At least one mean is different. Now, before we do the ANOVA and see how some of the calculations work and such, there are some assumptions we are making for the F test. And the F test, the F distribution, is what an ANOVA is based on. We are assuming that the population is approximately normal or sample size is large. Now, what is a large sample size? It's n greater than or equal to 30. Now, if you have small samples, there are ways to check for that normality, but for now, we're just going to go ahead and say it is approximately normal. The samples are independent of one another, so one group does not influence the other. The population variances are equal. That really just means the spread of the distributions are relatively the same. And the samples from each group are random, kind of a big thing that we've seen in most significance tests. So these are assumptions you should address in one way or another. But if you have these assumptions met, then we can do the ANOVA test. So let's go ahead and look at an example using the ANOVA. So I'm going to say I have data collected from three groups on the daily time the Alaska moose spends with his different contra-feeding items. So these were three items placed in the enclosure for the Alaska moose, and these are the number of minutes that the moose spent with these items. So we have water bottle, we have Lucky Charms, and we have something wrapped in seaweed. And these are all in minutes. So we have these three groups. We want to perform an ANOVA test to see if at least one of these pairs is different. We're really trying to see, does one stick out from the other? So if I wanted to do a hypothesis test, what I'd do first is I would assign each one of them a population mean. So we'll just go mu1, mu2, mu3. So mu1 is going to be the average time he spends with the water bottle at all times in his enclosure, and so on and so forth. So my null hypothesis is going to be mu1 equals mu2 equals mu3. And the alternative hypothesis is going to be at least one pair is different. And our goal eventually will be, if we can prove at least one pair is different, then we can go off and do some other tests to see which one is different. Now, when you're doing an ANOVA test, the very first thing you should do is you need to find the sample mean and sample variance of each group. So we're trying to find X bar for each one. And remember, variance is standard deviation squared. So if you were going to use your calculator to figure out the standard deviation, you would have to square that number. So I can find those here. I'm going to do X bar 1, X bar 2, X bar 3. And then I'll do sample variance 1, sample variance 2, and sample variance 3. And these are just numbers that I can put each data set in individually and find. So for mu1, I got a sample mean of 4.5 with a variance of 3.41. I'll go to 2 decimals for all these. For mu2, which is the Lucky Charms, I got a mean of 8.83. and a sample variance of 14.17. And for sample mean 3, I got a mean of 3.67 and a sample variance of 5.47. So if I look at this data just very informally, you can kind of see that the second mean is bigger than the other two. We just have to see, is that convincing enough evidence to say that that mean is different than one or both of the other means? So for most tests we do, we use the p-value method, but that is pretty difficult to do for ANOVA unless you're using technology. When we do the second example with technology, you'll see it's actually not so bad, but when you don't have the technology, it's kind of hard. So we'll use a traditional method and we'll use this F distribution that we can find a critical value. And then if our stat is bigger than that, then we'll reject. And if it's not, we say fail to reject. So to do this, we actually need 2 degrees of freedom. We have a degree of freedom of the numerator and degree of freedom of the denominator. So the degree of the freedom of the numerator we sometimes call DFN. Degree of freedom of the numerator is the number of groups minus 1. Well, there are 3 groups that we're doing, so that degree of freedom is 2. The degree of freedom of the denominator is the big N minus K. It's the total number of data pieces in all the groups. So if I count all the ones in all 3 groups, that is big N. So in that case, this is 18 minus the number of groups, which is 3, so that's 15. So from this chart, I can figure out which of these numbers is going to be my critical value. Now, if you look at the left side of this chart says degrees of freedom in the denominator. So on this first part of the chart, I do not see 15 for the denominator term. Okay, so here's the second part of the chart, and I'll attach a link to these charts. It's a big chart with every degree of free term you want. So here's 1 and 2. These are degrees of freedom of my numerator. So I had a degree of freedom of my denominator of 15. So I'm going to go over to 15 and I'm going to pick one of these. And what it gives me is it gives me a bunch of alphas. So whatever alpha I want, that's the one I pick. So I am going to pick 3.68 because I don't have an alpha. So I'm just going to go with 0.05 because that's always our default. So our F critical is 3.68. And then we're going to use that. We're going to calculate a statistic, an F statistic, a test statistic, and we're going to compare it to this number. So that's kind of the idea behind an ANOVA. Now, again, most of the stuff can be done with some technology, but we're going to do at least one of these examples by hand, just to kind of show you what actually goes into this test. So the first thing we're going to do is we're actually going to find what's called the grand mean. Because our whole goal now of all these next couple steps, and there's lots of steps, our whole goal is to figure out what is the F statistic. And then if that F statistic is bigger than the critical, we reject. If that F statistic is smaller than the critical, we'll fail to reject. It's just that simple. So the grand mean, what we're going to do is we're going to take the mean of all the data in the set. So for us, the X bar grand mean, we're going to add all the data and we're going to divide by 18. So I add them all up, I get 102.6. And then I'll, of course, divide that by 18 to get my grand mean. So I am going to get 5.7. So the average of all the data is 5.7. And that'll be used in one of the parts of our next part, trying to get this F statistic. All right, so to calculate the test statistic, we have to calculate 2 kinds of variances. The whole idea in an ANOVA, it's the analysis of variance. So we're using different types of variances to actually compare the means. So the first one is what's called a between group variance. So a between group variance, the formula is the summation of n sub I times x bar sub I minus x bar grand mean all squared all over k minus 1. Now, x bar of I is just each individual mean, so we have 3 different sample means. We're going to subtract them all from the grand mean, and then we're going to square it. multiply it by its individual sample size, and divide it by k minus 1, which is the number of groups minus 1. So sounds more complicated than it really is. So the bottom of this is 2, because we have 3 groups, and 3 minus 1 is 2. So the top, let's go ahead and start with the first group, which is the water bottle. Now, there were 6 data points in the water bottle group, and its mean was 4.6. So what I'm going to do is I'm going to take 6 times 4.6 minus 5.7, and I'm going to square that. That was our grand mean. Remember, the 5.7 is our grand mean. And then I'm going to add it to the next group. The next group is the Lucky Charms, mu2. So there was 6 in that group as well. The mean of that was 8.83 minus 5.7 squared. And then finally, we'll have 6 for the last one. And then we'll have its mean, which is 3.67 minus 5.7 squared. Now, if you're doing this with a TI calculator or some other calculator, always good to have the extra set of parentheses when you're figuring out what this is. So I would encourage you to try this, try to plug it in, try to see if you can get the same thing with me. Obviously, you can pause the video at any time you need. So I get 45.38. So that is our between group variance. This will also sometimes be called the MS. So when we look at the technology, if you see the MS, that's another way to represent between group variances. We'll have an MS for between group and an MS for within group. Speaking of within group, that is our next type of variance we have to calculate. The within group variance is the summation of n sub I minus 1 times the sample variance all over the summation of the n sub I minus 1. Now in this case, the bottom, it says the sum of all the sample sizes minus 1. Well, each one is 6, so I'm really just adding 5 3 times. 5 for the first, 5 for the second, 5 for the third, because it's 1 less than the sample size. Now for the top, it says take 1 less for the sample size, and then multiply it by its variance. So it's 5 times 3.40, or 3.41, plus 5 times 14.17, plus 5 times 5.47. So these are just multiplied. So that's going to give us our within group variance. So again, be very careful when putting this in the calculator. Put some parentheses around here and around here if you're going to put it just like that. But hopefully, if you get this, you'll get 7.68. And again, I'm rounding both of these numbers, but the within group variance and the between group variance are really the only two numbers you need to find your test stat. Now, to find the test stat, it's actually really, really simple. Now that you've done all the work above, all we're going to do is we're going to take our between group variance and divide it by our within group variance. So our F stat for this problem is simply going to be 45.38 divided by 7.68. So we're dividing these two crazy numbers that we did all that work to find. So 45.38 divided by 7.68 is 5.91. So now that we've done all that work, we're actually ready to make a decision. So the key is we will reject if the F critical value, well, I should say we'll reject if the F value is greater than the F critical value. And in this case, it is, because our F value is 5.91, and our critical value, which we found from that chart, is 3.68. So we will reject the null. So the null said that they were all the same. So if we're rejecting that, then we can claim the alternative, which says at least one is different. So my conclusion would be there is evidence to show that at least one pair of means Or we could say one pair of mean contra-feeding times, because that's what this problem's about, is significantly different. Now, this is kind of where the ANOVA test is different than other ones. So in this case, I've told you that at least one pair is different, but we really don't know which pair that is. Is it the first and the second and the first and the third, or some combination of those pairs? So ANOVA is one of the first tests we've seen where once you get one result like this, then we'll have to do further testing. And we'll see that in the next section next week. But for now, we know that at least one pair is different because we've rejected. Now, if I were to fail reject, our problem would be over. We'd say there's no evidence to show that at least one pair is different, and we just go from there. So this is doing it by hand, obviously quite a bit of work. Please watch the second video where we'll kind of go over this second example. We'll go ahead and we'll summarize the first example here, and then we'll go ahead and do a second example with the technology.